Hello and welcome to my demo on using 16 color sprites on the Nintendo DS. So let's get into it. So first off, what I'll do is I'll talk about the sprite capabilities and what actually comprises a sprite, and the different graphics bits and pieces that come along with that. So first off, the DS is obviously the successor to the Game Boy Advance, and as a result of that, it pretty much has all of the sort of hardware and some of the limitations that the Game Boy Advance had. For example, you still have the limit of 128 sprites, just like the Game Boy Advance. The only difference now is because you've got the dual screens, you have 128 for the top screen, which is called the main engine, and you also have 128 sprites for the sub engine. So you get twice as many basically. Obviously you can't sort of share sprites in between both of the engines. They're both basically separate mini sort of like game consoles, really, you could say, to some degree. They each handle the sprites totally separate than one another. You can sort of create a way to seamlessly move or appear to move sprites from one screen to the other, but maybe I'll cover how we can do that when I come to using 256 color sprites. So let's get into this now. So you'd use sprites in games for the main sort of player, really, or the main sort of game actors in the game. Unlike the tiled backgrounds, where the tiles have to be positioned aligning to 8x8 pixel tiles, sprites can pretty much be put wherever. They can seamlessly move into the screen from outside the borders, and they can move 1 pixel at a time. Also, sprites can be configured to be in various sizes other than 8x8. And then when you flip the sprite, the whole sprite size that you've configured handles arranging the tiles inside it so that the whole image flips vertically or horizontally correctly. So one of the things with sprites is they're referred to as objects on the DS and the Game Boy Advance. Hence the if you see any of the documentation, which I will put links and encourage you to actually have a look at, you'll see that they're referred to as OBJs. But there's sort of like separate parts of them. You have OAM memory, which is where you configure the properties, the sort of if you can think of them as like switches to set the sprites to do different bits and pieces. These properties have their own area of memory called object attribute memory, and then you have another separate area of memory which handles the color palettes for the sprites. So each engine has its own color palette. The main engine has a sprite color palette, which is separate from the background color palette. So the sprites can have 256 colors, or in 16 color mode they can have 16 palettes of 16 colors. And the sub engine's color palette is totally separate from the main engine's color palette, which is good because it means that you can have not only have totally different graphics, but you can also have totally different colors as well. So I've listed here the address in hexadecimal where the main engine object attribute memory lives. You got this one here, 700,000 is where the object attribute memory is, and then the color palette for the main engine is this number here, and then you'll see the sub engine address here in hexadecimal. So one thing to note is just like on the Game Boy Advance, the object attribute memory is 1 kilobyte in size, or 1024 bytes. Each sprite entry consists of 8 bytes. 8 bytes is 64 bits. So those bits are kind of split into parts for configuring various bits of the sprite, like its horizontal or vertical position on screen, or what priority it has when it's being drawn, which is over which background layers it will appear. And then there's like another one of the other bits controls whether it's in 16 color mode or 256 color mode. So I'll get down to some of the other property bits here. So like I was saying with the sprite sizes, they can only be configured to be certain sizes here. So you have, weirdly, you have like a shape setting and a size setting. And these are bit flags which determine this. So if the width and the height are the same, then it's assumed to be like a square size, whereas if the width is larger than the height, then it's wide, and then if its height is larger than its width, then it's configured to be tall. So one thing to note as well is the various parts that make up the properties of the sprite. There are limitations on the numbers. Two of the key ones to bear in mind is the horizontal position of a sprite can only be between 0 and 511. If you set that horizontal coordinate to higher than that, then that number will bleed into the other properties around and potentially cause various other glitches with that individual sprite, because the these numbers are grouped into like bit regions. So if you put a number larger than what can be held in that bit region, then you'll start interfering with other properties of the sprites. Just something to bear in mind there. And then some of the other useful properties that the sprite can do is you can flip the image horizontally or vertically via clearing or setting one of the bit flags. There is also the ability for sprites to be rotated and scaled as well. That's using what's called an affine mode, which is set up by other sort of bit switches, and I won't be covering any of that, but the links that I will give you will hopefully point you in the right direction should you wish to play around with that. And because lots of this is the same as on the Game Boy Advance, one of the links at the top here, the Tonc lib link, it goes into like a deep dive on using sprites, and lots of that will actually apply to the DS as well. Although some of the structures that they use on the Game Boy Advance to do that in the Tonc lib is is obviously not used on the libnds for the DS. I'll get into some useful code that I've created to handle working with sprites and make it a lot easier there. So before we can use sprites on either of the engines, we obviously need to create our graphics for them, and then we need to convert those into tiles, and then we need to make sure that we've also got the color palettes for those as well. So I recommend using my graphics converter purely because it makes working with converting your graphics and creating your graphics, you know what you're getting, you know where you will be putting the colors, where the colors will be laid out, etc. Whereas if you use grit or the whatever other sort of graphics converters which are available, if they don't output the graphics in an easy accessible form to you, then you might not be able to configure the graphics how you would like to, which is why I wrote my own image converter, if you like, and I would recommend using that. I will only be referring to that in my sort of demos. I won't be going on to any of the other ways that you sort of can convert graphics. So one of the other things with the DS as well is when you set up the sprites, you have to tell whichever engine you're using how the graphics is going to be laid out in VRAM, as well as you also have to tell the engine which VRAM banks you are actually going to use for graphics. Unlike the Game Boy Advance, the DS does not share its sprite tile graphics with background tile graphics. Instead, there's like areas in memory where you have to tell the engine which VRAM bank you want to map to that area, just like you did with the 16 color background tiles. If you've not watched that video, then you will need to watch that video to get a better understanding of sprite graphics, because it pretty much uses the same format for as the 16 color background tiles. So one of the things we need to do is when we set up sprites is not only do we need to say how the tiles will be laid out. I always choose the 1D layout, which basically means that when you convert your tiles, each 8x8 tile is laid out in sequence in memory, rather than as a shape via the 2D format, which I won't be going into here. But again, on the on Tonklib's site, he'll discuss all of that, which I won't be covering here. And then one of the other things to note as well is just like on the background modes for setting tiles, the tile range can be between 0 and 1023, so you can actually access 1024 tiles. The sort of the sprite parameter that allows you to change your sort of tiles allows that range. On the weird thing is with in the backgrounds mode with background tiles is you still had to arrange tiles in 16K blocks, but in 16 color mode you could only in one block of 16K you can only see or access 512 tiles, whereas to use all 1024 you would have to have two of those 16K blocks right next to each other laid out in VRAM. One of the things I'll be showing later on is how to convert an image that fills the full screen into tiles to use as a background, and that uses 768 background tiles. I'll show you that in a bit, and you would obviously need to have two regions right next to each other to be able to sort of do that. So getting back to sprites now, so when you set up this this 1D layout, you have the option to choose. Let's open up some. So you have the option to choose either 1D 32, which means you're using 32K of VRAM for sprite tiles, 1D 64, so you're using 64K, and you can use 1D 128 as well, which would use 128K for sprite graphics. However, the sub-engine can only use 128K. So if you wanted to use 256K, then you can only do that with the main engine. Again, there's kind of disparities between what the main and the sub-engine can do. So when you set the banks for sprites, the sub-engine can only use bank I or bank D for sprites. So notice the size there. Bank I is only 16K in size, so that limits your sprite tile number to the amount you could have on the Game Boy Advance. If you needed loads of sprites for the sub-engine, though, you can use bank D. Or obviously, if you use bank D for sprites, then obviously you won't be able to use it for backgrounds. So there's give and take with all these things there. So loads of this here is just sort of some of the theory. I'll go into more detail in a moment, like on all of these things here. So some of the useful structures which DevKit Pro provides for us working with sprites is the OAM table, which is it's a structure which is set out to fill the whole OAM memory area with an array of sprite entry structures in there, and also an array of affine structures, as you're limited to how many sprites you can actually rotate if you choose to have sprites that you can rotate. So I think there's I'm not going to cover any more here. I think I've said enough about all of this. You'll probably learn more from actually playing around with the sprite stuff yourself. So let's I'll show you the sprite entry stuff first, and then I'll go into some demos, and then I'll go into some graphics. So the key thing with sprites I'll just set this up a minute so we can see everything here. So to be able to see the internal structures, we obviously need to uncomment this here, and I'll open that up in a moment. So what I have in here is I have two sort of separate function setups here. We have one load of functions here for handling sprites on the sub engine, and then we have a load of useful functions here for on the main engine. Hopefully you saw the last video on tile graphics. If not, then you will want to watch that first. So we have functions here for setting are palettes here. So these are palettes of 16 colors. I won't be discussing the formats for these. They were in the 16 color tiles video, which is relevant to this one. And then one of the things I've created here is like a useful structure to remember some of the settings that we have. It's probably not that useful in this program here, but for your future programs it could be very useful. I chose not to allow access to the main arrays here, so all we're sort of doing each update is when something's changed, we are updating these parameters here. So the tile base is basically the starting tile. So when you I'll get into some stuff here now. So these are some custom graphics which are an alternative graphics to the players here. I'll go over how we can convert these to use in this program in a moment. So one thing to note is everything is still tiles when it comes to sprites. They are still made of 8x8 tiles. So whenever we want to draw the sprite, we need to know where the top left tile number is. And then in the 1D linear layout, which is what we're using, it then expects all these tiles to be in a row after each other. So they would be laid out in video RAM like that. That would be tile 0, 1, 2, 3. That would be 4. That would be 5. So the graphics converter that I use handles all of this for us as long as you put in the size of your graphics frame. So to go into what these how we're sort of doing these, we have this structure here for the main OAM table. So this table here, if I open this up, so you'll see here this is a union. So what that means is these two things, these two arrays here basically are mapped on top of each other, which means that they both share the same memory footprint. And then you'll see here the sprite entry here. So if you hover on here, you'll see that the sprite count is 128, which is the maximum amount of sprites that the DS can actually have. So this table here is laid out in such a fashion that we can copy it over one of the OAM memory regions, and it will map all of it into the right places for us. So then if I come up to this other structure here, this big structure here, which looks scary and confusing and will take a while to get your head around, you'll see that there's lots of structures and unions all embedded in one another here. And this is the this is how the DevKit Pro sprite entry union makes it easier to work with sprites, believe it or not. If you see the if you check out the Tonc website and have a look at his documentation on the sprites, you'll see all of there's like 4 attributes per sprite, and that's basically for unsigned shorts or U16s. Basically, as I was saying with the sprite properties, there's like 64 bits in underneath each of these, and these structures group regions of bits together. So you'll see here the Y coordinate. It says it's a U16 here, but what this flag here says is only use 8 bits. And then you'll see this boolean here for whether the sprite should be shown or hidden. Usually the size of a boolean changes depending on which console it's being the compiler is building it for. In this case, it's saying use only 1 byte here. And then you'll see here only 6 of these bits are set for this hidden unsigned char. So in all of these structures here, all of the bits which handle different parts or different properties of the sprite has been handled for us to allow to work with it in an easier fashion. But obviously, to look at it straight off, it's kind of a scary sort of mess and kind of confusing. It's not until after you've worked with these things for a while that you discover the usefulness of them. So we basically have 2 of these empty structures here, one for the main engine here, the OM list, and one for the sub engine, and then I'll record how many are actually in use each time. And then what we have is we have an array of these structures here. And one of the first things we have to do is after we've told the main and sub engine that we wish to use sprites, I'll show you how that's done in a moment. So if you've seen the last one on tiles, you would have saw that these flags did not exist before. So to use sprites on each of the engines, you have to first say what layout and how much memory the sprites are going to use. And then you have to use another bit flag to say activate the sprites on that engine. If you check that out, you'll see a list of available options here. So I didn't actually set up the amount of RAM that we'll be using, but it doesn't really matter, to be honest. I don't think it will matter if you obviously try and put a load of sprites in, a load of graphics in. You will obviously need to set some of these to go for anything other than the sort of default size of 32K. So by not putting this in, it actually defaults to this, because you'll see it's 0 shifted by 20, which obviously is 0. So we start off, we set both of the modes, we tell them we're going to use sprites, and then we need to call the sprite manager init function to initialize the sprites. And all we're doing here is we are using the we have to set a VRAM bank for the graphics area in memory, where VRAM must be mapped into to be able to use that graphics. So in the case of this demo, I'm using bank E and bank I. And then I call the sprite clear function with either true or false. True to use to clear the main one, and false to clear the sub table of sprites. The only reason why this function's in here is to basically clear them all away, or hide them, disable them, whatever you want to call it. And how it's doing that is there's two defines here. In the video previously I said where the areas of memory are. These defines basically are labels that point to those regions here. So OAM is has the memory address of the main engine's object attribute memory, and OAM sub holds the sub engine's memory region. And then all I'm doing there is basically copying one of these OAM buffer arrays onto either the object attribute memories region or the sub object attribute region, and we're just hiding the sprites and disabling them. So once we've done that, then you first have to set the graphics and colors for our sprites, and then to use them you call either sprite main new sprite or sprite sub new sprite, and then you specify the width in tiles and height in tiles. So that's the width in tiles in pixels, so that should only ever be either 8, 16, 32 or 64, and the same with the height as well. The tile base is always the starting tile number, and then internally we record the tile base, and then when you update the sprite later on with a new position and frame number, it will then work out internally where the new tile for that graphic should be, as it will have recorded the size previously. And we'll just make things a bit easier. And then I have like a second function here for updating everything of the sprite. And then we also have some other functions here for flipping its image horizontally or vertically. So if we are looking here a minute, and I'll quickly show you the what's actually going on behind the scenes there, which is the important thing there. So first off, we work out the how many tiles are actually in one frame. So if you remember from this picture here, you'll see our character Barrio here is he's made of 4 tiles. So you would pass in his width and height as 16 by 16, and then internally this then calculates where the starting tile would be based on the tile base, which needs to be the actual tile start, and the frame number, which is literally just, once you've got the tile base, you can literally just treat the frame as if it was an image frame, as in the we have 2 frames of animation here, so that would be 1 frame, and then that's another frame there. Then make sure that we've not overflowed the amount of sprites. Obviously we're limited to the sprite count of 128, so if you try and do more, then it'll throw an error there to help you out. And then the same with setting some sizes up there. And then all we are doing then is we using the sprite main count, we then access the main sprite array, which is our array of Sprite 16s. Our POAM here is a pointer to a sprite entry, and then all of the main sort of sprites live in an OAM buffer array. So we basically use the ID number of the sprite main count to get the array offset for each of these. We then add 1 to the sprite count at the end here to say we've added a new one, and then we basically set these up in this structure here, and then we then sort of mirror those in the sprite entry here. So the sprite entry is the actual bits, if you like, in which will be written to in OAM. So we set the color mode there. It can obviously be either 16 or 256. I'll get into 256 color sprites in another video. And then, as I was saying, the one of the sprite entry functions here is the X and Y positions. You'll see that they're referred to as U16s here, but that is not the case, as there are limited bits in the 64 bits which a sprite has that you can actually use for the horizontal and vertical. In the case of the sprite, what I do here is, if its X coordinate is greater than the width of the screen, then we put it at the width of the screen. So it'll basically be hiding just outside the right hand border. If you do not clamp the X and Y values, then the bits after the X and Y will be corrupted with the screen positions, and all kinds of other glitches will occur, which I had first off mucking around. I forgot to put these in, so put them in. And then we at the start here, I didn't bother putting in the flipping the images at all. Obviously these are all just references. Once you know how these all sort of work here, then you can obviously just create your own functions with whatever you kind of need for your own specific game, really. This is just kind of like a template to show you how to use them and get started. And the key one in here is the graphics index in the sprite entry. This is the where the TileData will start, and this is a number, not that, it's a number between 0 and 2003. And then the other thing which I said you have to do is you have to set up the shape and the size. So these compare groups here kind of do that, if you like. If the width is greater than the height, then we have to set the shape to be in wide. If the height is greater than the width, we have to set the shape to be in tall. If that isn't the case, then it's obviously square. And then once we've set the shape, we then have to set one size. And then that's that then. And then what we return is the actual number we've just set up of the sprite. So then in all future updates, we just pass in the number which is returned here, and then the X and Y position and the frame number, and then that handles all of that nicely for us. So what I'll do now is I'll show you what this actually does. Oh yeah, I have to comment that out. Doesn't like that for some reason. Okay, so now we've done that. Now I'll finally show you what the program actually is. So one thing to note is this is kind of a faux game to some degree, or a mini game you can call it. So one of the things that I'll go into in a minute is how I created the background here. So the background is actually an image converted into 16 colors using the awesome GIMP graphics program here. We convert that into 15 colors and then tell that to use there's a couple of different differing patterns that it can use when it converts it to 15 colors. So you'd have to play around to find whatever works best for you. So after the main title screen there, we have a choose player screen where you can use the D-pad left and right to choose whatever player for your game you want. Then press start again, and then you've got a wave of different baddies to defeat. They start off slow on level 1. The peaks and troughs of their movements are random. So there's a number of different waves of them per level, and they basically speed up. If you die, then you fall down like that, as I'll show you again. There you go. So it's got all the collisions that you need for a faux game in here. You'll see at the bottom on the sub screen I'm updating the score and the lives. And then also note that as the background is not seamless horizontally, we get this line as we're scrolling the image over and over again horizontally. We need an image that is seamless. I'll go over creating that in a moment, as I have a number of different backdrops I've played around with. So I'll close this now, and that will give you something to play around with and test out. Some of the states I've added here is the choose player states, which is if you add more into your games, it's literally just a case of add some more main states for the main loop, and then you want to add some more external initialize and run functions. And then I always just add a GS for game state to the front of those. I'm not going to go into any great detail on any of these other things, because obviously this is about sprites. But all of the code, I'd advise you to go in and have a play around how all of it works. The main interesting one is obviously the baddie manager code here. This has everything you will need pretty much. We have a initialize, reset, update and render function here. And if you go through and see these, you'll see how the sprites are basically handled we have this game actor structure. All of the actors have a state. They're either dead, dying, or normal. Obviously that should vary depending on whatever game you have. And then you'll see we record the sprite ID in there. And then in here I have two other useful structures which I usually always use as well. We have the rect structure, which is basically a rectangle. And then to hand over collisions, we have this function here, rect overlaps, which basically compares the position of two rectangles and returns true or false. So I won't go into this in any more detail. I will come back to this code when we or rather when I cover music and sound effects, as the game kind of feels naked to some degree without any music or sound effects. So what I'll go into now is creating some graphics. So if you wanted to add your own characters in here and your own custom backdrop, then what you would need to do is first off draw them. I recommend using Sprite, but obviously you can use whatever you're comfortable with. And then whatever colours you end up using, create like a top row here. And then you can then use this colour palette here to work with and draw in your characters. One thing to note on the DS as well is all these colours should be in steps of 8. Obviously 255 isn't, but that's the maximum of the red, green or blue range that you can have in a byte. And then once you've created your frames here, so they should be 16 by 16 pixels in size. Once you've done that, save your image as a PNG file. And then what you want to do is you want to make sure that you've got my DS to tile converter program. Check out the videos. There'll be a link in the tile converter video. I think it's there's one for the Game Boy Advance. It also does the DS as well. And then you'll go into the release folder, double click that, and then leave it in 16 color mode. Make sure you have it set to image palette at top left, and then you want to put in the size of your frames. So in our case here, we're working with 16 by 16 pixel ones. And then if I move this in here, so they're next to each other, just drag it across. You'll hear a beep. It'll tell you how many colours it's found, or it will tell you that there's graphical errors if you've messed up. If you click the left mouse button, it will zoom in, and then you can use the, if you have a middle mouse button, you can hold that down to move the image around. So the left mouse button zooms in. Holding the middle mouse button, you can drag the image around. The right mouse button will zoom out. And then once you've done that, just click on save and then select wherever you want to put that. And then it will tell you, although it says 4 tiles, that's actually 4 image frames. You can specify it to separate the different areas into groups of how many 8x8 tiles there are in there. So if you save that again now, and then navigate to where you saved that, and if you open that in a text editor, you'll see this is our color palette here converted for us, and this is our graphics for our images we just created, laid out in the correct order for us to just load into VRAM. Now if you look at the other one, you'll see the difference there is it's commented out and spaced the frames into 8x8 tile region parts. This would be useful if you're playing around with players, if you like, or maybe enemies, or some sort of graphic that you're not sure whether you're going to keep it in your game or not, or you want an area to be highlighted like this so you can cut and paste different frames in and out of a graphic array. So then once you've done that, create another C file, or just open one that we already have, and then come down to an empty spot. And then one of the things I've already done is need to set up an array where your alternative player graphics is going to be. So you'll want a U16 for the color palette and a U32 for the tile data. And then in the source file, just to copy across your color palette, like so. This is exactly the same, by the way. And then do the same with your tile data. You see that I already commented these out in the exported data, so we can literally just plot that in there, and then that's already, because that's commented out, that will obviously not interfere with the actual data there. And then save that file, and then in the main source file here you'll see there's this is where we set up the tile graphics at the start of the program, just like in the other video I did on 16 color tiles. So we'll comment out those, and then what we'll also do as well is we'll change the backdrop as well. In fact, no, I'll do that in a minute. Actually, I'll do that in a minute. So let's build that, and then come back to here again. Here we go, press start, and there we go. Here's our new players. Simple as that. And then go in here, you can then go on a shooting spree then with right. Let's fix that backdrop. So one of the ways that you're going to create new backdrops is you'll want to try and find an image online. So if I boot up a browser here, like just type in probably best to go for a HD one actually. And then as we're going to be converting this to 256 colors, sorry, 16 colors, or in fact rather it's going to be 15, because one of those colors will be the background color. So you want something that's not got too much in there. So we could pick this one, looks like it could be okay. Find like whatever you want as a backdrop. I've already got some examples that I will be showing here. So once you've got your picture, what you then want to do is, one way to accomplish this is we want our image to be seamless horizontally. So one way to do that is we can select 128 by 192 image part that we would like to maybe turn into a backdrop. And then what we do is we then paste half of it in here. So what you do is you create a new image 256 by 192 first. Then you would paste in this is a larger image, that's why. So this is one I was working with first off. So you basically you paste half of it in, you then mirror the image, and then you kind of try and align them up. So you end up with something that looks like that first off. And then what you want to do is then double the width again of the image by resizing the canvas size. So if I put this back to 512 there. So we have this image here, and then we want to see what it would look like next to itself again, as we're going to be scrolling it horizontally. So we then double the width and paste it in again. As you can see, the if this scrolled across here, then obviously it would then appear on the other side of the screen, coming in the other border. Kind of looks okay, but it kind of looks a bit noisy, as in if what we would have to do with this image is we would have to scale it. Probably best not to scale this in Sprite, but instead to use GIMP to do your scaling and stuff in, as it's got some better functions to handle all of that in. So if you look at this picture here, so I'll come back to this picture again. So you'll see that the picture itself is low quality. It's very grainy. I don't know if you can make that out from the video. If I zoom in one time, you can see all the noise around. Now if we copied this into GIMP here, to paste that as a new image, and then what we want to do is we want to convert that into an indexed image, and we want to use 15 colors. We can't use the 16th color because one of the colors in the palette has to be a background color. And then you'll see here we have some differing options. We can either go for none. If you do that first off, we end up with this one here, which looks kind of messy there. There are ways we could probably fix that, but I'm not going to go into that. So then we can try a different one. So we'll go for normal. That doesn't look too bad. Still a bit of noise there. So that could probably be presentable. Although obviously at the moment this isn't seamless horizontally. And we would also have to scale this image down. So we won't be using this one anyway. But that was just showing you what to sort of look out for there. So this is me playing around again, like, so you could select part of an image like that, or another thing you could do is get like another sort of background like this, and literally you can just take like a segment of that and then use that segment as like a repeating tile or a texture. And then you would just, so what I'll do is I'll clear this out first. We'll take this again and then I'll show you how you would do that. So you want to create an image which is the same size as one of the DS screens, which is 256 by 192. This is our segment, or our texture if you like, which is 64 by 192. And all we're going to keep doing is flipping it horizontally. And the reason why you're doing that is because two of those borders will line up perfectly, as you can see here. Now we can select both of these, copy that, mirror it again, and paste that other one in. And here we have a seamless background. The problem is because this image was so low quality, as in the as you can see, it's obviously been saved or created maybe from a JPEG image, because they tend to have settings in them to save memory by having like a poor quality, or maybe the picture itself wasn't properly focused when it was actually snapped. So we'd have this here. So if we copy this and then bring it into GIMP again, paste it as a new image, and now if we convert that, you'll see that we have some kind of, almost looks like a interferent noise. The gradient doesn't kind of look right. You kind of get like a C-like pattern there, but the yeah, that's not that great. So you can play around with the other different modes. Sometimes some look better than others. Now I think that looks slightly better than the last one, but still not that great. And then the last one. So you'll find that some images work with one of the differing things over others. Yeah, this one's still not that great, so I wouldn't really want to use that one. So this was some other experiments I did with parts of the iceberg image there, which didn't really work. Again, you take parts of them and then mirror those horizontally and try and put them next to each other to see how they look. This one didn't look too bad, but not that great. And you can actually repair some of these images. I'll show you an example here how you can repair some of them. and remove some of the noise. So if we zoom in, and what you want to select is the smudge or blur tool, and then select like a blurry sphere there, or circle, sorry. And then what you can do is if you zoom in, and then you can use blur to kind of remove some of the noise from the image, which can obviously give you better looking images when you convert them. So this is how you could fix some of these noisy, poor quality images. And then what you'd have to do is play around for a bit until you've got it how you think it would be fine, and then convert it and then have another look. Kind of doesn't look too bad. One thing you could do though is we'll undo that. This kind of looks distracting here, so you could you can blur these, take one image and kind of use the blur tool to kind of fix some of this so it doesn't look like these are two halves of the same part. So using the blur tool we can remove some imperfections, if you like, as well as make it so that the image doesn't look so much like one half mirrored. That doesn't look too bad. It looks kind of better than what it did, I think. Anyway, that's just one thing you could do there. This is one of the backgrounds which I found which looks fine. This is what this is one I found which kind of looked okay. I took half of this image, as I'll show you here. So here we go. This is the original image here, and you'll see that I took the size is 256, which is the size of the screen. But that's because I basically cropped the original image to this size, and then I literally just took half of it in the end. Which is another thing you can do, is take half of the image. So you want 128 by 192. Copy that. Create a new image, 256 by 192. Paste that in, then mirror it. And there you go. So you don't have to use the same edge either. Select that, delete that. That one works as well. So once you've got a background that you want to use, pop back into GIMP, paste it into a new image. There we go. And then just play around with the dithering to see what one works best. That one's pretty noisy, so we won't go with that one. Okay, looks kind of better. You might have to zoom out to try and get a better feel for how it will actually look on the DS as well. I think that would probably be fine. So then other things you can do in here, which is quite useful, is you can play around with changing the various parts in here. This can sometimes give you some different results. And then there's always a colorize one here. So those are just some ideas that might be useful to you. And then once you've got the image that you want, save that. Close all of these. And then what you want to do is come back to our DS to tile graphics converter. And you want to leave that at 16 colors. Don't set a size there. It will automatically pick up the size from the image. And then you don't want to have image palette at the top left. You want to use this one here, image palette from image. Oh yeah, another thing you want to do as well is if I come back in here, if I open up the recent image, where is it? Is it that one? Nope, it's not that one. This is an image that's in there though, by the way, which I was going to show you in a minute. Okay, let's come back in here. So one of the things you want to do is the top left here, put a random color in there, but it needs to be in steps of 8, just like the everything else. This color here will be treated as the backdrop color. Basically, the graphics converter, how it works is it starts from the top left and then it goes across and then picks up each color as it finds it and stores it in the color palette for the image. So then you'll save that with that other color in the top there, and then you'll get rid of that when the once it's been converted by changing that 1 pixel in the first tile. So then drag that across. It will then scan the image. Oh, it's done there. So there we go. That's our backdrop. Save that. And then it should have 768 tiles. And then what you want to do is go to where you saved that. Open that up in a text editor. And then you'll get a huge load of tiles. And then this first tile here is the one where we set that background pixel. Now, one thing to note is that background pixel is actually the first one, which is set to 0 here. So change that to 1. And then what you want to do is put these side by side. Is you'll want to create another source file, and you'll also want to give it a definition in here. So palette and graphics backdrop, just like you did for the other tiles. and then you're literally just going to be plopping those colours in the palette bit there, and then drop all the tiles into your backdrop tile array there. Oh, you'll see here I forgot to do the there we go, didn't prepare that in that one. Now once you put your new backdrop in, all you need to do is then select it in here. So find the relevant set tile data. So that was backdrop 3. And then look for your palette one. I think that's backdrop 3. Yep. There we go. And then build that again. And then here we go. Here's our new backdrop. Select our player, and then you'll see that the it scrolls seamlessly across. So one thing you could do in your own program is have it so that you might have a different backdrop each level. I haven't done that in this demo. Before I end the video here, I will show you the second backdrop. And here's the second one. There we go again. And this one's seamless as well. It takes a bit of effort to get some noisy images to tile seamlessly. But once you've been playing around doing that for a while, you know how it works and how to get the best results. Right, I think that's it for this video. I'll leave links to the DS documentation. In fact, I'll open it up in a browser and show you so that you'll know why you need to check it out. So the first one will be the Game Boy Advance one I'll show you. This link here, so you'll want to go to regular sprites, and then you'll scroll down here and it goes into the you can disregard the memory region here. The key stuff you're going to be interested in is how he talks about the 1D and 2D mode there for tile mapping, and then this is the setup that they use on the Game Boy Advance. What we're actually using on the DS is the sprite entry structure, which basically does the same as this, except it obviously gives us access to the relevant bits with other sort of parameters for us to use rather than this. But this goes into the underlying bits for each parameter and what they actually do. So you could even use this instead of the sprite attribute, but sorry, the sprite entry, but I would probably stick with the sprite entry. But this will give you more info on what's actually happening there if you want to check that out. And then this other one here, is useful here. So this gives you a rundown of the technical details of the DS. There you go, that's the 2 chipsets inside it. Gives you the main RAM, work RAM, the some bits and pieces about the screens and the all sorts of other useful stuff, and the memory as well. So very much recommend checking that one out as well. So thanks for watching, and that's it for this video. Let me know if you've got any questions below, and I'll get back to you when I'm on next. Right, thanks for watching.